All right, I will begin with a word of prayer once I get up here. Dearly Father, we thank you for this day again. I thank you for this class, for calculus, that we can understand it. Help us to understand a little bit more about u-substitution today. Help the students to ask good questions as they think of them, Lord. In your name I pray, Lord Jesus. Amen. All right, so let's get straight into it. Unless there's a question about something, I will hopefully announce the homework list soon. I was going to do it last night, and I just got distracted, apparently. So I will try to bring a diversity of examples here today. I will use some of the homework problems for this purpose. Example 1. Suppose we're trying to find the integral of the hyperbolic cosine of the square root of x divided by 2 times the square root of x dx. What do you guys think we should do with this right here? U equals the square root of x. I like it. If we do that, then du is dx over 2 square root of x. Oh, hey, so this is straight up the integral of cosh of u du, which means we can integrate. We get sinh of u plus a constant, which is the hyperbolic sine of the square root of x plus a constant. There we go. 1 down. The marker's dead to me. Oh well. Let us try another. How about, let's see here. Yeah. Example 2. Suppose we're up against the integral of the cosh of phi d phi divided by sinh squared of phi. Any suggestions? So we're doing u-substitution today, if you guys hadn't figured it, yeah? Mm-hmm?
I was thinking.
Oh, okay.
I was thinking, can we take out like a 1 over sine h?
Take out? What do you mean?
Because you know sine squared, sinh squared.
Okay. I mean, yeah.
Use it as a constant, so it would be.
Oh, but it's not a constant. That's the thing, is we're integrating over phi. So like that's not a constant. We can't pull it out of the integral. Yeah. I mean, that would be nice, you know. Hey, listen, if instead of this I had like a dx here, then yeah, sure, you could just be like x cosh phi over sinh squared phi. I'd be right there with you, right? Assuming that phi is a constant, sure, you could do that, right?
That's not what I'm saying.
Oh, okay. I'm sorry. Let me not. So what were you saying?
So you know sine squared, you can say it's like sine squared plus sine, right? You know you can factor out sine.
Uh-huh.
If you want to sine.
Oh.
Yeah, that's what I'm saying, because it's a sine squared.
Excuse me.
You can make that a constant.
Oh, okay. You're thinking about using this thing? I mean, that's the identity between cosh and sinh.
That's not what I was thinking, but.
Yeah. But you're thinking too hard. First of all, let me put this back to phi. Listen, anytime we have something that's, so if you've got, you got to think about a couple different choices. Like I could make u equal to cosh phi. That wouldn't be good because I need to make every goodness gracious, every one of these we have to substitute the integrand and the measure. We have to get rid of the dx and the f of x, so to speak, and trade it for an expression in u and a du. So here, the denominator is kind of the trouble, right? So like, if I let u equal to a sinh phi, right? Then this will become, well, this down here is u squared, right? What's du? Derivative of sinh is cosh. So that's cosh of phi d phi. Wait, so that means that we're literally looking at du over u squared here with respect to that substitution. So what's the integral of 1 over u squared? One over u? That's almost right. Yeah, negative 1 over u. You got it. Excellent. So then we just go back to undo our substitution. So we got 1 over hyperbolic sine of phi plus a constant. There you go. That's all there is to it. So what would have happened, just for giggles, let's think about what would have happened if, now this is not what you were saying, but, just for idle curiosity, for curiosity's sake. What would have happened if we'd used that identity, What would have happened to us? Well, we would have had the integral of cosh phi d phi divided by, so sinh squared apparently is cosh squared phi minus 1. Yeah? And yeah, then I'd have been stuck, because I wouldn't know what to do with that. Let's look at some others. Example 3. See if you guys can figure this one out. Suppose we have the integral of 2 to the x times the cube root of 7 plus 2 to the x dx. Any ideas? You're going to say, you say let u equal to 7 plus 2x? Yeah, 7 plus 2 to the x. I like it. I think that's going to do it. Du will then be natural log of 2 times 2 to the x dx, right? The derivative of 2 to the x is natural log of 2 times 2 to the x. So this here, I can see that 2 to the x dx is equal to du over the natural log of 2, right? So I can trade out this guy and that guy for a du over log 2. So I've got the cube root of u times du over natural log of 2. Let me rewrite this as the integral. Let me pull the log over 2 out front. Now that we can do, right? That's a constant. So we've got integral u to the 1/3 du. Hey. I'm sorry, guys. Well, I say I'm sorry, but I'm not really. I mean, I'm powerless to stop it. You're like, well, you could just stop class for a week. Well, I mean, I could technically. We're a little bit ahead. We probably still finish, but I'd really rather give you the last couple of days of class off
Oh, what you mean?
to study. What's that?
You talking about during that?
Hmm?
You talking about during that?
Like the very end of the semester, we'll probably wrap up the material like a couple days early. So you guys should have a couple days of study. That would be my goal. Right? Assuming I don't get sicker, so I end up having to take a day off and stuff like that. But all right, so what's the integral of u to the 1/3 is u to the 4/3 divided by 4/3, which is give us 3/4 times u to the 4/3 plus a constant. And then let's finish this thing. So 3 over 4 log 2 times 7 plus 2 to the power x to the 4/3 power plus a constant. There you go. Does that make sense? I hope. All right, let me give you guys something to chew on here. Example 4. How would you integrate x dx over, let us say, 3 minus x? Ah. What do you guys think? Oi. Make u equal to 3 minus x. That sounds like a good idea. Let's see if that helps. If we let u equal to 3 minus x, then du is minus dx. And so we've got integral of x times minus du divided by u, right? And then what? What's the rub here? We can't just turn a blind eye to the x, right? Like, we got to deal with it. How do you deal with it? Oh, I think what you're telling me is to solve this for x. Is that right? So if I solve that for x, that gives me x equals to 3 minus u. So what we got here? We've got the integral of 3 minus u times minus du divided by u. Yeah. Oh well. Which is also known as the integral of u minus 3 divided by u du. We can simplify this further. What's algebra tell us? 1 minus 3 over u du. Can you guys integrate that? What's that?
Si, senor.
Si, senor. Es bueno. Via con Dios, mi amigos. Let's see here. U minus 3, natural log the absolute value of u plus a constant, right? Don't forget your absolute value. It is absolutely needed. And so the u is 3 minus x. So what you got here is 3 minus x minus 3 times the natural log, the absolute value of 3 minus x plus a constant. There you go. Excuse me. Yep.
Can you bring just the x down and then just distribute to the 3 minus
Bring the x down?
From the start of the equation. So you have x to the first power. So bring it to the denominator. Then taking x to the negative 1, distributing that to 3 minus x, and then integrating that way.
Well, if I brought that to the denominator, like, all right, so let's think about that here. So I've got x over 3 minus x, right? So you're kind of asking the question, how can we just simplify it? I think if I bring x downstairs, that looks like this. Right? Which then gives me 3 over x minus 1, which is different. I just don't know what to do with that, like from an integration perspective. You can't integrate fractions as like a fraction of the integrals. It's not the case. Like, we have no theorem that says like the integral of a fraction is the fraction of the integrals. Like, it doesn't work that way.
Okay, but in this example, if you were to look at then that portion of the question is 3 over x as just being 3x to the negative 1. Can you then just move that up to the numerator?
I mean, look at this as x times 3 minus x to the minus 1?
No. Looking at it as 3x to the negative 1 minus 1. Or, yeah.
3, say that again, 3x to the what?
3x to the minus 1. Minus 1.
Minus 1? Is that, I guess the question, is that equal to x over 3 minus x? Oh, the answer is no. We can't do that. That is not an allowed, like this, these do not cancel like that. That's bad algebra. Like, it doesn't simplify that way. So, so like, all right, so like x over 3 minus x is equal to x over x times 3 over x minus 1, which is 3 over x minus 1. So like, in order to factor x out of the denominator to make the cancellation that you're thinking about, I have to have an x in both terms. I cannot just cancel. It is not an allowed algebra step to like cancel this and that. Like, that is not a legitimate algebra step, if that's what you're saying.
Okay, yeah, that makes sense.
Mm-hmm.
Yeah.
Right. This is a very good question, because we like if you need to get that out of your system, right? Because that's an untruth, and it's going to hurt you if you keep it, you know. So you need to like kill that thought somehow or another. But anyway, we've all done this, of course, and you have lots of company doing that. I've graded the test. This is a popular wrong algebra step, so. Oh man, goodness gracious. Let's try another. How about, I will tempt you again. X squared over 1 plus x squared dx. So what we cannot do, right, is cancel the x squared. Yeah. But I guess if I see somebody write the answer like x over 2, I would know where they're coming from. Because if you cancel the x squared, it'd leave you like a half, and then you'd integrate to get x over 2. So like if I saw a student write x over 2 here, they're probably doing that wrong. Anyway, but we can't do that. X squared don't cancel. How do you deal with this? Let me show you how I deal with this. I do a sneaky step. My sneaky step is this. I add 0. Now the reason I did that, and you can add 0, right? The reason I did that is because now this is equal to the integral of 1 minus 1 over x squared plus 1. And you might say, well, this isn't really a u-substitution example. Aren't we doing u-substitution today? Well, yeah, but not always. All right? And more to the point, do I tell you on the test, this is a u-substitution problem, this is a not u-substitution problem? No, I just give you a list of things to integrate. So one of the things that you have to get good at is identifying what's the right tool to use on a problem. That is what makes tests like way harder than homework. If you do homework from the book, it's all nice and compartmentalized. The problems on that technique are in that section, right? This is one of the reasons that physics books are better than math books in some regard. Because at the end of the physics chapter, you have problems from the whole chapter. It doesn't tell you which part of the chapter to use, right? So there's an intrinsically more challenging aspect to physics homework in that regard. Mathematicians have made it like little bite-sized chunks, you know. Anyway, I shut up. That we can integrate, right? The integral of one is x. The integral, and the other one's just inverse tangent of x plus a constant. We don't need u-substitution here. We just need algebra, right? Let's see here. Let's try something similar but different. And I'm not sure this is going to go well, but we'll try it. Example 6. What if I had like integral of, I don't know, x cubed over 1 plus x squared dx. Now I just made this up. We might not be able to do this. I don't know. I mean, I'm not sure this one we can do. We're going to try. I can write problems for differentiation down with reckless abandon, and we can do them because you can differentiate anything. It's just a product of product rules and quotient rules and chain rules. But if you just make up a problem to integrate, there's no guarantee that you can actually undo it. All right, like it's much, much more dangerous. I'm hopeful maybe we can make, maybe we can make u equal to 1 plus x squared. Let's try that. Let's see if we can, let's see if we can flesh that out. I'm going to try. U equals 1 plus x squared. Right? So then du is what? Du is 2x dx. So we've got x squared and then times 1/2 du divided by u squared. Do you see what I did there? So like x cubed dx is what? Well, let me be less weird about this. Let me just solve for dx. This is a good place to solve for dx. Dx is equal to du over 2x. So I've got x cubed times du over 2x. Let me simplify that. That gives us 1/2 the integral of x squared du over u squared. Again, x squared is not our friend. We must have only u's. What's that? Oh, you're like you can solve. Yeah, I think you're right. So we can trade x squared for what? X squared equals to what? U minus 1. U minus 1, all right. So I think you guys are up to my trick. That's good. Great. And let's simplify that. So we got 1/2 integral of 1 over u minus 1 over u squared du. And if you don't mind, I'm going to do a little serpentine calculation here. So 1/2 natural log the absolute value of u, parentheses in the 1/2, plus 1 over u, I think, right? See what you guys think of that. If you differentiate this, if you differentiate that, does it work? Well, the reciprocal function is natural log the absolute value of u. We've talked about this before. That should be familiar, right? If I differentiate the reciprocal function, aw man. If I differentiate the reciprocal function, I get minus 1 over the square function, right? So I think that's good. And now what's left? Go back to the meaning of u. natural log of absolute. Now I don't really need absolute value because x squared plus 1 is necessarily positive. And then plus 1 over x squared plus 1 plus a constant. There you go. Whew, well, that's a relief. I wasn't sure we were going to get through this problem when I wrote it down. But it turned out okay, right? All right. What's that? Oh, where's the end of the parentheses? Still in the marker. There you go. So, yeah, thank you. That's a very good question. All right, so something else we need to talk about. U-substitution. With bounds. You got two choices. You can either work it out, then apply FTC2, or you can change the bounds. Them's your two choices. Not changing the bounds and writing them incorrectly is not a choice. That is a way to get me to take points off. So let me tell you show you what I'm talking about. Here, example 7. Example 7. For instance, we might have the integral, let's say from, I don't know, 0 to 1 of x squared dx over x1 plus x squared, right? So work it out, then apply FTC2. Can we work out the antiderivative of this function? What do you think? I mean, I hope so, right? It's like right there in the middle board, right next to the example, right? We just did that one. See it? So apply, and we're done, right? We got what? Basically your big F of x. Man, all my markers are dying. Excuse me, I'm not coughing on you guys, I promise. All right, so we do x minus inverse tangent of x. You take that thing, evaluate from 0 to 1, so that is equal to 1 minus inverse tangent of 1 minus 0 plus inverse tangent of 0. That is equal to 1 minus pi over 4. So there you go. That was option 1. Option 2 is to change the bounds. Let's look at that. So here's how that goes. Integral from 0 to 1 of x squared dx over 1 plus x squared is equal to, basically we're going to, oh man, well that was just dumb. Well, I didn't make a u substitution to do this. Stink. No, I can't. Sorry guys, poor planning on my part. I can't really illustrate option 2 here because it's not a u substitution, right? Duh. Sorry. This illustrates what I'm talking about for option 1, but in a dumb way. Let me try to do better. Okay, so example 8. Notice the integral of 2x e to the x squared dx is equal to e to the x squared plus a constant, right? This follows from a u equals x squared substitution, right? I think we worked this out like last class. Okay? Great, so that's that antiderivative right there. Great. If I integrate this from 0 to 1, then I can do e to the x squared evaluated from 0 to 1, which will give me e to the 1 minus e to the 0, also known as e minus 1. there you go. That's the not changing the bounds way. Oh man, I have the worst luck today. Oh, look at, Dope. All right, let me fix it. Let's go from 0 to the natural log of 0 to the square root of the natural log of, you guys pick a number, any number, make it positive though. 10. 10? All right. 0 to the square root of the natural log of 10. So square root of the natural log of 10. So that gives me what? E to the natural log of 10, because the square root of the natural log of 10 squared is just natural log of 10. E to the log 10 is 10 minus 1. The answer is 9. The reason I need to change the bound is for the u substitution here, there's no change if I make a u equals x squared substitution. So like, here we go. Excuse me. Integral from 0 to the square root of the natural log of 10, 2x e to the x squared dx. I promise I'll give you a better example here in just a minute. We let u equal to x squared. So du is 2x dx. But when we have bounds, we also have to change the bounds. So like u of the square root of the natural log of 10 is equal to the square root of the natural log of 10 squared, if I'm making a u equals x squared substitution. So that simply simplifies to the natural log of 10. On the other hand, u of 0 is 0 squared, which is 0. See, if I had kept my bound as 1, I would have changed bounds from 0 to 0 and 1 to 1, which would have been, I mean, this is bad enough that the lower bound's not changing. So here it goes. Integral from 0 to the natural log of 10 of e to the u du. And so that is e to the u evaluated from 0 to log 10. In other words, e to the log 10 minus e to the 0, which is of course 10 minus 1, which is 9. So these are the two different methods of calculation. The one method is to find the antiderivative, use FDC2. The other method of calculation is to change the bounds according to the u substitution. Let me see if I can come up with another example which is a little bit less awkward. Sorry guys. All right, here we go. Let's try this on for size. Example, what am I on? Example 9? Excellent. All right, so suppose we're integrating, say from pi squared to 4 pi squared of the sine of the square root of x over 2, oh my bad. Let me think about this for a second. Well, we're just going to take it wherever it goes, it goes. All right. We'll see where it goes. I may have done the opposite thing that I want to here to make it pretty. If so, I'm sorry. It is what it is. I should probably just look at my homework and work some of those if I was smarter. But, well, you guys know already. So we should make a u equals to square root of x substitution. Yes, that would be nice. So we let u equal to the square root of x. That makes du equal to dx over 2 square root of x. So see, with that u substitution, we have sine of u du. But we must change, so once you change from dx to du, if we're dealing with a definite integral, we must change the bounds. Or you have to do an indefinite integral and apply FTC2. All right, those are your two choices. What is u of 4 pi squared? That's the square root of 4 pi squared, also known as 2 pi. What is u of pi squared? It's the square, hey, I did something smart, yay. It's pi. All right, so my bounds change from pi squared to pi, and from 4 pi squared to 2 pi. Hooray. And what's the integral of sine? It is minus cosine. So we have minus cosine of u, lower bound pi, upper bound 2 pi, FTC2 here. And so we've got what? Minus cosine of 2 pi, minus minus gives me plus cosine of pi, which is what? This is minus 1, also known as minus 2. They're both negatives. They don't cancel here. Any questions? Do you guys understand the issue here? If you're working a definite integral, you must change the bounds. All right. I said yesterday that we'd circle back and do another one of those tricky completing the square things where both issues came up. So let's do that now. Let's do that. So just so you know what we're doing, tomorrow we'll be starting into how to integrate trig functions. I'm going to share with you things about trigonometry that you do not know. Why do you not know them? Well, it's simple. You were taught by people who are afraid of complex numbers. I am not afraid of complex numbers, and I will share with you the many things that have been known about trigonometry in complex numbers for, well, about 300 years now. But for some reason, they're not commonly shared in the pre-calculus course because we want to make sure students have a more complicated way of understanding something rather than having the easiest way, which is with complex numbers, believe it or not. So I will show you a method tomorrow which will allow you to derive trigonometric identities that you don't know. You can literally use algebra to work out trigonometric identities. That's what we'll see tomorrow. And we'll need those in order to integrate trig functions. We need a complete mastery of trigonometric identities. Basically, trigonometric identities plus u substitution allows us to integrate a great vast number of examples of trig functions. So example 10. All right, and I'm going to give us a break from the bounds. We'll come back to the bounds in time, but that's enough for now. Let's get back to the indefinite integration. What do you do if you got something like this? X dx over x squared minus 6x plus, oh, I don't know. Let us say, what's that?
36.
36, no, that's too easy. Well, actually, is that too easy? No, that's just fine. I'll take your 36. Let's do that. All right. So what then? What are we going to do? I would suggest we should complete the square in the denominator. First of all, you can't just make a u equal denominator substitution. It won't work, will it? Right? It doesn't quite work. I mean, you could try that and see where that takes you. We could do that. I mean, we could make a u equals denominator substitution. And if we did that, it would produce, do you want, let's try that out. That's kind of a weird way to do things, but if I let u equals to x squared minus 6x plus 36, that makes du 2x minus 6 dx, right? And goodness gracious. So if you use your imagination, and if you got a significant imagination, you can see that this is, well, I mean, by golly, this is a factor of 2 out. All right, fine. I'll allow it. 2 times x minus 3 dx, great. So, I mean, this is 1/2, parentheses 2 times x minus 3 divided by x squared minus 6x plus 36. Yeah? If you do what? What do I owe you? I mean, the 2 and the half cancel, that leaves us the x that we got there to start with, right? But I just subtracted a 3. To be fair, I must add a 6 inside the parentheses. So 6 over, you know, x squared minus 6x plus 36 dx. So, all right, so with respect to that, I got myself a 1/2 the integral of du over u plus the integral of 3 dx over x squared minus 6x plus 36. So I'm like, well, okay, great, but so I'm still stuck with this thing, all right? I'm going to erase this. Let us start again. Okay? It didn't work, right? If you want, we could continue on with this. Do you want me to not erase and just go on? I think we're going to have better chance of success here if we just... Sorry, guys. All right, so here we go. Integral of x dx. Complete the square downstairs. I have x minus 3 quantity squared. I take away 9, but I've got 36 here, so plus 27. All right? And then I'm going to do something rather sneaky. I'm going to trade that x for x minus 3 dx plus 3 dx divided by x minus 3 squared plus 27, which will give me 2 integrals. It gives me x minus 3 dx over x minus 3 squared plus 27 plus the integral of 3 dx over x minus 3 squared plus 27. Both of those we already know how to do. Oh, how do I know that I know how to do these? Oh, well, I mean, factor 27 out. Oh, actually, this one, I can just look at that. That's 1/2 du over u. This one, factor a 27 out. I got a 3 over 27 integral of dx over 1 plus x minus 3 squared divided by 27. So I've got 1/2 natural log the absolute value of u plus 1/9 the integral of, let's let w equal to x minus 3 over the square root of 27. So then dx equals square root of 27 dw, which gives me square root of 27 dw over 1 plus w squared. And so the answer is 1/2 natural log the absolute value of the denominator, which was x squared minus 6x plus 36. Sorry, I'm out of time, guys. Plus square root of 27 divided by 9 inverse tangent of w. But the w was x minus 3 over the square root of 27 plus a constant. Now, I'm sorry, hopefully we'll have more time to talk about one of these another day, but this is what happens with a quadratic in the denominator. If it's irreducible, you get two pieces. The one is like a log, and the other piece is an inverse tangent. If the quadratic in the denominator factors, other things can be done, but we learn about those in calculus too. Something called partial fractions comes into play. But we don't teach that this semester, so pretty much I'll only focus on the case that the denominator is irreducible. If the denominator could be factored, something else special has to happen this semester. So anyway.